Hey everyone! Thank you so much for watching this paper review video of GEPA, Reflective Prompt Evolution Can Outperform Reinforcement Learning. Before diving into the details of the GEPA optimizer and exploring how it works, let's start off with the takeaway that's made in the title of this paper. Reflective Prompt Evolution Can Outperform Reinforcement Learning. So why is this so interesting? I think this is pretty counterintuitive to most machine learning engineers, and I think this is sort of the counterintuitive finding of these large language models as optimizers in this whole space, is that there's just so much performance gain to be found in optimizing the prompt or the way that you present the inputs to the large language models, even so far as this is outperforming directly updating the weights of the neural network, the parameters of the large language model, with these sophisticated algorithms like GRPO, DPO, and this kind of thing, of showing that GEPA and MIPRO are outperforming, directly updating the weights of the neural network. So I think this is a huge thing to kick this video off with, is to just sort of motivate the interest in these prompt optimization algorithms and seeing how far we can explore with this. And that's not to say that this is completely mutually exclusive either. We're definitely going to see these kind of hybrid algorithms that combine this large language model as optimizer with direct gradient descent. And this is one of the most interesting findings and sort of insights from the authors in this paper, is the way that they compare the prompt optimization as these coarse-grained jumps along the optimization space compared to gradient descent being these fine-grained movements in the optimization landscape. One of the best examples of the subtleties of these prompt optimizations is found in the unreasonable effectiveness of eccentric automatic prompts. The authors are benchmarking large language models on the GSM 8K benchmark for mathematical reasoning. This is where the large language models are given tasks like, Jim has 8 apples and he gives 2 apples to Alice. How many apples does Jim have left? And then all sorts of variants like this with more complex math that's done in the reasoning, and generally to assess how well large language models can do mathematical reasoning. So in the real world, say you've given a large language model an agentic system, your taxes or say stock options, and it's got to reason about math in order to produce its answer. So what they're finding is that by adding this to the prompt command, we need you to plot a course through this turbulence and locate the source of the anomaly, adding this kind of affinity for Star Trek results in the large language models performing better at mathematical reasoning. So this is a more extreme, nuanced example of this, but generally just the way that we phrase these tasks to the large language models has a huge difference in how well they can perform at them. So hopefully you're now convinced of the power of the prompt, leading us to the next question: how do we find these prompts? So this whole space of automated prompt engineering was really kickstarted by this super exciting insight of using the large language model to propose prompts for large language models and building these agentic optimizers or compound AI systems for optimization of compound AI systems. This is this super kind of meta learning, exciting thing that's emerging out of all this. But to set the stage for this, large language models as optimizers presented the ORPO algorithm, which is using an LLM as the mutation operator in evolutionary optimization or genetic programming, where you start off by having a candidate of solutions. In this case, say you have 20 different prompts, 20 different phrasings of the prompts, and then you have some kind of selection criterion like the score they receive on some task. And then what you do in ORPO is you format each of the prompts and the score they received as the input to the large language model to then produce a new prompt. And the idea is that the language prior, the reasoning ability of the large language model is able to try to take apart which parts of certain prompts are performing well, which sort of prompts are performing well, and it's a really strong prior on how you're then going to propose a new prompt. And in this paper, again, just another anecdote of how surprising these findings are. Let's work this out in a step-by-step way to be sure we have the right answer. Achieves 58.8% accuracy, whereas take a deep breath and work on this problem step by step is achieving 80.2% accuracy. So this is just another testimonial to these insane jumps you're getting by finding these particular prompts. So another perspective, in addition to language models and evolutionary optimization, was to bring in Bayesian optimization and Bayesian search into searching for the optimal instructions, as well as few-shot examples. So in this class of solely optimizing the prompt to improve the performance of large language models, in this video so far, we've been discussing changing the instructions, the way you describe the task. But you also have few-shot examples or in-context learning, where you might give a few examples of the task in the input to help the large language model understand the task. So MIPRO is based on the insight that there might be some combination of instruction with few-shot examples that as you're enumerating through all these possibilities is in, as you do with these black box optimization algorithms, that results in the optimal performance. So say you have 10 different candidate prompts, as well as 10 different few shot examples, 10 different examples, and you're trying to find like some combinatorics of, say, example 1, 7, and 9 with prompt 2 compared to, say, prompt 7 with example 3, 4, and 5. So you're doing that Bayesian search between the combination of instruction candidates with examples. And it also introduces some new ideas that sort of are then advanced a bit in GEPA, like the program aware proposer. So MIPRO is using the specification or the DSPy signature in order to decompose the task and use this to give hints for proposing new instructions, as well as a dataset summarizer looking at your training data set in order to extract these kind of hints that are all generally kind of used to guide this prompt proposal step, the input for the for the prompt proposal, which is a very interesting sort of inception of this, where you have an AI system optimizing an AI system. Now let's dive into how GEPA works. Similarly to OPRO, GEPA uses a genetic optimization loop and is about interfacing LLMs with evolutionary optimization. So you have a population of candidate prompts, you have some kind of selection criterion, then you have some kind of mutation or crossover operator to produce new prompts or new candidates, and then you loop so on. So in OPRO, they primarily innovate around the mutation layer, having the LLM produce new candidate prompts by looking at the performance of the past iteration of selection. GEPA is going to introduce two key innovations for interfacing LLMs with genetic optimization. The first of which is Pareto-Optimal Candidate Selection. In mathematical optimization, a Pareto frontier is used to optimize multi-objective loss functions. So say you have a performance metric like accuracy, but then you also have a cost metric like, say, the size of the neural network, or say it's just the number of input tokens, things like this. You have this, you're balancing performance with cost, or you have different measures of performance. And that's the general idea behind Pareto optimal. It's like a Pareto frontier and that kind of idea. So the way they're using it in GEPA is to organize the candidates and their selection probability. So instead of just greedily selecting the prompt with the highest average score as input to the mutation, or say only using the top 5 prompts according to their average score across all your training samples, they're going to use your training samples to create a Pareto frontier where any candidate on the frontier outperforms the other candidates on at least one of your training samples. So let's say you have 8 training samples and you currently have 3 candidates, A, B, and C. And A outperforms B and C on 5 out of your 8 training samples, whereas B outperforms A and C on 2 and C 1. So now you're going to use that 5 over 8, 2 over 8, 1 over 8 as a part of the weighting for which ones you're going to sample to then pass into the mutation operator, and how you're going to explore the tree of candidates. So if you say you're at 0 and that's just your initialization step, and you produce 1, 2, and 3, and 1 has the highest average score, so probably it also outperforms across the samples. So you're more likely to select 1, or in this case, it's also, because it also is like a random probability. So even though it had the highest probability, you still happen to have selected 3, and then from there you produced 4, and now you have your new frontier of this 1, 2, 4, and you selected 2 to produce 5. But the way you're doing the selection is kind of hard to capture in this kind of diagram particularly, but you're maintaining the Pareto frontier and the selection probability based on outperforming on particular training samples you have. So let's take a little bit of a detour on the general motivation of this kind of candidate selection algorithm and the paper that the authors cite from 2015, Map Elites. Map Elites is about quality diversity algorithms. It's one of the early pioneering works in this space that was really driven by scientists such as Jeff Clune, Ken Stanley, Joel Lehman. There are all sorts of amazing works on quality diversity, which has now also been kind of merged with open-endedness, and there's some great research from, say, Google DeepMind on that. But I think there's a little bit of difference in quality diversity and open-endedness that maybe we can talk about in a second. But this general space of quality diversity algorithms, I think, is just one of the most exciting areas of artificial intelligence. I think it's really exciting for Weaviate as well, the use of vector embeddings to measure diversity, and also I think something really interesting with the evolution of the Weaviate transformation agent. But to firstly explain what Map Elites is. Map Elites was about the morphological design of robots. And you have these different decisions, like, say, where you want to put the motors, or say the amount of force that they can apply in the motors. And also, I don't know too much about robots, but all these kind of things. And so what you're seeing in this plot is you have 2 different features. So say it's just like max force, and this is like 10 to 30, and then you have some point here, which is like 10 feature 1, 30 feature 2. And this is the best performing, say the fastest robot overall, if that's your performance measure. So generally the idea of, avoiding local optima, to take even a further step back, is say we're currently at this point in our optimization landscape, and we're following the gradient up this hill, and then boom, we're at this local optima, we're at the top of the hill. We think we found the best possible solution. That's generally the idea behind this whole kind of optimization space, is trying to maintain these diverse points so that we don't just hill climb up to a local optima, and we can instead explore the entire space. But imagine having, instead of maybe like hyper particular feature 1, feature 2, we have a compressed vector embedding, say with UMAP or TSNE, and then we have this way of looking at our population of, say, we have an LLM that's writing all sorts of different poems, or say it's generating art, and we have this way of exploring all these different candidates. I think this is such an exciting future for understanding creativity in AI, and I think it's really exciting to see it, of course, used in this context of ensuring diversity in the candidate instructions used for prompt optimization. All right, so now it's time for what I think is the most exciting thing about this paper. As mentioned in the title, reflective prompt evolution. So let's start off by decomposing this prompt and then step a little more into the individual components. This is the prompt for proposing a new instruction given one of the current instructions, or the mutation operator in our genetic optimization loop. I provided an assistant with the following instructions to perform a task for me, and then you input the current prompt, the current instructions at this step. The following are examples of different task inputs provided to the assistant, along with the assistant's response for each of them and some feedback on how the assistant's response could be better. So this is already a huge novel innovation with this. You're providing the list of the inputs, outputs, and then this is the thing that is completely brand new about this, is the feedback for the mini batch of examples. Let's maybe take a quick detour into this feedback concept. So typically with optimization, we have some kind of metric, like say in information retrieval and search, we have a numeric metric like the recall, the number of gold documents that were retrieved by the search system. And we would return this 0.7 score, and we're trying to optimize, say, our embedding model, or say we're weighting the alpha in our hybrid search, or we've got a re-ranker, all these things that we do as we're turning the knobs and trying to optimize our search system, but we're using this scalar feedback signal. Now, the whole idea of these language models as optimizers is that language models have such a strong prior on language. They can reason about language. And so instead of interfacing our metrics as numeric scores, we can have numeric scores as well as natural language feedback about what went wrong with this input-output sample, or what went right about it. So in this particular case, we've asked our search system, how does hybrid search work? And we just receive, if we're only using numeric rewards, we just receive 0.7. That's what you have to say the quality of the search. But in this new paradigm, we have the natural language feedback. The retrieval system successfully retrieved documents about dense and sparse search encoding algorithms, but failed to retrieve documents about indexing and rank fusion algorithms. So we have the particular feedback for what went wrong, and again, or went right, that we can use in order to reflect on the current instructions. So we have our current instructions, and then we have these inputs and outputs that are produced by the inference with these instructions, and then the feedback from the metric of what happened with that particular input and output. Say it's an instruction for how to decompose a query into subqueries. Then again, we have inputs like how does hybrid search work, and then we have the outputs, or however you're going to interface that, and then we have the feedback of what happened, and it's able to integrate this as it's proposing a new instruction. So then finishing it up, your task is to write a new instruction for the assistant, and then just kind of some more about how to do this, and then the formatting for the new instruction. The next really exciting thing they do with reflective prompt evolution is to have this as a structured output, where in addition to the new instruction that's proposed, you also have a rationale or a summary of what's different about the new prompt. And what this lets us do is easily inspect these lineage trees as the prompts evolve. So we start off with this base instruction. This is for the I think PUPA task of privacy preserving queries. So we start with the initial prompt of, given a private user query, create a privacy preserving request for a powerful external large language model. The LLM may assist without learning private information about the user. And then when we're extending it to this new prompt, we have a summary of the update, expanded privacy strategies and task understanding, and then a summary of what's different about this new prompt. Adds detailed guidance on identifying and generalizing PII, stresses analyzing query intent, and introduces reasoning explanations for reformulation, and so on as we continue down our tree during our GEPA optimization process. So the authors also present this system-aware merge as a strategy for, I think, jointly taking advantage of this tree structure, as well as this general idea of these multi-layer language programs. So probably throughout this video, at least for me narrating it, it's felt like we're mostly thinking about this as a single prompt for a single inference. But generally the scope of this is that you have a compound AI system that has, say, 4 different inferences. And so when you're doing the reflective prompt evolution at each step of the tree, you're really selecting one of the 4 modules to update with this prompt. So as you kind of generalize this from a single prompt to an entire compound AI system, you have yourself quite a more difficult optimization process. And so that's kind of what the system-aware merge thing is doing, is looking at how you can take 2 different candidates and sort of look at their lineage of the mutations along each of the, say, the 4 modules and how you're going to merge them. So definitely a lot to this, and I think this will be a future direction as you evolve from optimizing just one inference to an entire system that completes some really complex tasks through all these inferences. Now let's put these components together to walk through how the GEPA optimizer is going to find the optimal prompt for your task. We start off by initializing a candidate set of instructions for the task. So say this is some hyperparameter of the GEPA optimization algorithm. Say we have 10 candidates to initialize, and then we'll have this natural kind of pruning with our Pareto-Optimal Selection that we'll dive into in a second. So then we have our budget of how many times we're going to loop through the genetic optimization process of selection, mutation, selection, mutation. So now we're going to dive into our candidate pool. So say we initialize, in this case, 5 different prompts, P0, P1, P2, P3, and P4, and say we have this kind of tree structured lineage in our initialization where we start off with P0, and then P1 and P2 are derived from P0, and P3 and P4 are derived from P1. So now we're going to construct our Pareto optimal frontier by evaluating on our training samples denoted as tasks in this visual. So say you're training a search system and you have, in this case, let's say 3 you probably have more than this in a search system case, but say you have 3 different queries that you want to test the models on. This could be, how does hybrid search work? This could be, how do I deploy Weaviate with Kubernetes? And this could be, how does HNSW and product quantization work together? So now you're going to see which of your candidate instructions performs better on each of these particular samples. So say in this case, you got recall 0.95, 0.9, 0.85, and so on with these other ones. And that's how you organize your frontier of the best performing candidate for each of your training samples. So now that you organize your candidates this way, you construct the Pareto frontier. So we're only going to be sampling now from either P3 or P2 because they're performing the best on our Pareto frontier according to some tasks. So P3 is on the Pareto frontier because it's performing the best on task 1. So now we're going to pass either P3 or P2 depending on how much sampling we're doing, or sampling P3 each of them multiple times probably in this case. And we're going to pass them into our reflective prompt mutation operator or our system-aware merge between 2 of our candidates to produce new instructions P new. So now we're going to evaluate this new instruction and we're going to see if the performance has improved. If not, we're going to discard it. If it has, then we're going to add it to our pool and then recalculate the Pareto frontier across our training tasks with this new candidate, say derived from P2 or P3. And then we're going to loop for as many times as our budget allows. Let's dive into the experiments that were run in the paper and some of the key takeaways from the authors about understanding the GEPA optimizer and what happens on these different benchmarks. So the authors are going to report the performance on 4 benchmarks: Hotpot QA, IFBench, Hover, and PUPA. So as a quick background on this, the authors are going to be building off of the LangProbe benchmark. LangProbe is a collection of pre-built compound AI systems for different tasks like coding, reasoning, agentic tasks, RAG, knowledge, information retrieval, as well as classification and mathematical reasoning. So each of these specialized programs like Generator, Critic, Ranker, this is a composition of DSPy module, well, I guess you call it an implementation of a signature or module, but of DSPy compound AI systems in DSPy that do things like, say, the multi-hop summarize. It will it'll take a query and write a new search query from it, and it'll summarize the search results. So these are pre-built chains of multiple LLM inferences in service of completing some tasks. So they're going to build off of this for these benchmarks: Hotpot QA, which is like question answering, IF bench, instruction following, hover fact verification, and PUPA, which is privacy preserving information retrieval. So the first key takeaway, as kind of we've already talked about in the title of the paper, reflective prompt evolution is highly sample efficient and can outperform weight-based reinforcement learning. So this is the high-level overview of on the latter end of the regardless of the sample efficiency, but of the performance on these different benchmarks. You see that GEPA is at 20 points better than Hotpot QA, and this is a super impactful information retrieval. Search is obviously a huge market and something that we've done plenty of at Weaviate, but this kind of being able to find this 20% improvement is absolutely massive. Similarly, you see gains in instruction following, fact verification, and then privacy preserving information retrieval. So these are the results on the Qwen 3 8 billion parameter open source large language model, which really helps you study this the difference in GEPA and GRPO and direct gradient updates. They also present the results on GPT 4.1 mini. So this might be, I'm actually not sure where the state is of which of these is more interesting for most people out there, but this is generally kind of, I think, how most people think about these prompt optimizers. Weight updates isn't really even an option unless you're using, they have these kind of like fine-tuning APIs, but anyways. So these are the gains that they're finding on GPT 4.1. Again, Hotpot QA, just a super impactful real-world task, 38 to 69. On the other hand of the sample efficiency, this figure is showing the number of rollouts required to achieve different scores performance during the optimization process. So not only is GEPA outperforming GRPO or say direct weight updates with I think GRPO is the cutting edge reinforcement learning algorithm for doing this. It's also able to do it in less rollouts. It's more sample efficient during optimization. So I think this is one of the most interesting insights from the paper is the comparison that they're making for prompt optimization and this kind of prompt proposals with language models in the kind of optimization landscape perspective. So when you're doing gradient descent, again, you have some kind of gradient that you say you're right here on the optimization landscape and your gradient is pointing this way. So you move the weights of the neural network in this direction to get the performance up the gradient. And now you have your kind of your local optima that you're stuck on in this case. What they're saying is that when you do a prompt proposal with the language model, this is able to take you from say here to here, and this kind of idea of having these coarse jumps in the optimization landscape, whereas gradient descent is only able to make these kind of little movements compared to big jumps in the prompt space. So I think that idea is such an interesting one about using the language prior of the language model to navigate this optimization landscape. So I think we're also going to definitely see kind of cases of using the prompt optimizer to jump from here to here, and then you're using the gradient descent hill climbing around this kind of new region you found in the space. This kind of, I think just this perspective really helps you think about what the evolution of this kind of prompt optimization as well as gradient descent might be. And this is another quote I really like kind of reacting to this paper. It's totally plausible that a model could get IMO gold without any reinforcement learning given a perfectly crafted prompt. We just don't know and lack the tools to efficiently search through prompt space. So I think this is a great perspective on this. Like, we really don't know how far we can take this prompt optimization, and it's really interesting to think that we can get such performance gains just from changing the instructions alone. So the next couple of takeaways are around the comparison of only tuning the instruction, the description of the task, compared to few-shot example optimization. So the first takeaway, reflective prompt evolution enables instruction optimization alone to outperform joint instruction and few-shot optimization. And then similarly, it's computationally cheaper and generalizes better than few-shot demonstration prompts. So this is particularly illuminated with their comparison of GEPA with MIPRO, the previous state-of-the-art in the DSPy optimizers, that's looking at this joint tuning of instructions with few-shot examples. So I think this is definitely interesting, and obviously these are the results that they're showing in their paper, but I think there definitely is a bigger picture going on with the kind of few-shot example landscape that's worth sort of keeping an eye on. So I really think this work from Google is interesting towards compute optimal many-shot in-context learning. So Google is making these huge advances in long context large language models, which means that you can put many shot in context learning. So rather than a few shot, they're talking about having, say, 500 examples of the task directly in the prompt. And they're particularly looking at some interesting strategies that we're, of course, interested in at Weaviate with using, say, a vector search to populate related demonstrations to the task. But so I think there's definitely a lot of nuance here. But I mean, obviously, what they're showing with GEPA compared to MIPRO is, makes that claim interesting, but I think there's definitely a lot of emerging stuff in this space of in-context learning with examples. The next key takeaway is diving into the next candidate selection strategy and ablating the Pareto-Optimal sampling compared to just greedily selecting the highest performing candidate at each iteration of the genetic optimization loop. So you see the high-level takeaways across the benchmarks here, and they show all these different trees of showing how the Pareto-Optimal selection is able to get out of these local optima and overall explore the space. So this is such an exciting takeaway for these quality diversity algorithms and the strategy of having an algorithmic mechanism like this Pareto frontier across your training samples, which is super interesting in itself. All sorts of this kind of training data distribution and this way of explicitly organizing it this way, such an interesting direction for the future of these systems. So finally, the last takeaway is about the system-aware merging. It seems like they're still kind of working this out and figuring out how to balance the reflective prompt evolution mutation with this kind of crossover step and merging the two candidates together. While most of this paper has been focused on optimizing compound AI systems using some kind of training data set and validation data set, the authors conclude the paper by exploring using GEPA for inference-time search. So inference-time search describes searching for, it describes all sorts of different methods of this kind of scaling test time compute. There are all sorts of different ways people are defining this. Most commonly what you're referring to is scaling the amount of inference used in chain of thought. So chain of thought is where you have, let's think step by step to achieve this task, and typically you have some rationale from the model before you then complete the task. And models like, say, OpenAI's O3 and all these kind of things, they have reinforcement learning on this reasoning step, and then they'll control how long it reasons for. So maybe you have 4,000 tokens of first reasoning about the task before then answering it. But then test time scaling could also refer to generally this kind of compound AI system thing where you could have, say, like the network of networks approach, where you have 1,000 inferences and then you take the best of n. So you're kind of like ensembling all these inferences. That's kind of another way of looking at it. Or, yeah, generally this kind of compound AI system where you decompose a task into all sorts of subtasks, and so you have like these reflection steps that reflect on the current answer. So there are quite a few ways of defining this kind of test time scaling thing. But one of the most interesting probably is this kind of training at test time, where you're actually updating the model as it's like navigating through a new training instance. So there was a really famous paper from MIT on this. I'm not sure if this is that one particularly, but in this paper, the surprising effectiveness of test time training for few-shot learning, they're looking at this kind of, you have this input and you're using data augmentation to create new samples, and you're updating the model essentially this way by having this training at test time. So what they're showing with using GEPA as a training inference time search strategy is that you start off with say you have a task where you have a verifiable reward. This is also like one of these emerging terms in AI is reinforcement learning with verifiable rewards. So say you're completing a programming task, all sorts of programming tasks. In this particular case, you're optimizing kernels for, I think, CUDA kernels, as well as kind of AMD thing. I don't know too much about this particularly, but you have that direct feedback that comes from the compiler when you're optimizing code. So you can use that as a signal to search for solutions. And so instead of just searching for solutions by sampling many times from the same neural network, which is a super common strategy with this kind of like rejection sampling, oversampling, all that kind of stuff. But what they're going to be doing is they're going to be using that same GEPA tree search strategy that we've been looking at to update the instructions during inference time. So you're getting your signal back from the compiler as well as this metric feedback, because the compiler typically will give you a stack trace if it's, say, completely failed, or you'll get, say, the performance of the CUDA kernel you just optimized. So you can use the same algorithm to be updating the instructions as you're navigating just with a new inference. So you could use this for really open-ended tasks to kind of separate this reinforcement learning with verifiable rewards thing from like any arbitrary task. Generally, you can use some kind of, say, LLM as judge as a proxy to get this kind of signal and similarly do this. But this works extremely well when you have such a concrete signal like the compiler output. Thank you so much for watching this video explaining GEPA. Reflective prompt evolution can outperform reinforcement learning. Hopefully from this video you have a better sense of the core innovations in this paper, such as the reflective prompt mutation and the Pareto-Optimal Candidate Selection, and overall this space of interfacing large language models as optimization algorithms in this genetic programming framework. If you're interested in learning more about this general space of compound AI systems, optimizing compound AI systems, I highly recommend this talk from Omar Khattab at the Databricks Data Plus AI Summit, DSPy 3.0, and DSPy at Databricks. I also really hope you'll subscribe to our YouTube channel. We have some really exciting projects coming out of using DSPy and Weaviate together. And again, I really hope you found this video useful. Thank you so much for watching.